12.5 and 12.6 continued. We're going to look at a couple distance formulas. We can calculate, for instance, the distance from a point to a plane using some very simple vector computations. And we can do the same thing for a line, but we're going to start off with a very simple example with a plane. And I'll explain what these symbols mean here in the distance formula. Well, first of all, we want the distance from 1, 2, 3 to x plus 2y plus z equals 1. P1 is 1, 2, 3. That's the P1 right here. P0 is any point in the plane. So we can pick some random point, P0. There are a lot of choices here. We just simply need to find something that satisfies the plane equation. A very simple point, for instance, could be 0, 0, 1. Simply because 0 plus 2 times 0 plus 1 equals 1. I could have used 1, 0, 0. I could have used 5, 0, negative 4. 5 and negative 4 is 1. It could be any point. This formula is actually based on a projection. It looks a lot like the projection formula. We're actually going to project this vector onto this normal vector. And that gives us this formula here. So we could work through this by finding this normal vector that comes right from the equation, finding P0, P1, projecting that onto that, finding the magnitude of it. And we would end up getting this formula right here. But it's a lot easier just to write out the formula. Now we have P0, P1, and we can construct a vector. I'll do that over here. ABC, that's simply the normal vector from the plane. That comes from these coefficients. And so I'll write that right here. ABC equals 1, 2, 1. Now all we have to do is compute. Let's write all this down here. P0, P1, the vector from here to here, 1 minus 0, 2 minus 0, 3 minus 1. That's 1, 2, 2, and I'll write ABC. It's good to write it over here where our work is. 1, 2, 1. Now we have to calculate a dot product. This, by the way, is absolute value, not magnitude, because the dot product gives us a scalar. It's just possible this could come out negative, depending on how our vectors are configured here. And P0, P1 dot ABC is equal to 1, 2, 2 dotted on 1, 2, 1. Well, guess what? That's 1 plus 4 plus 2, which is equal to 7. And then we can find magnitude A, B, C equals magnitude of the vector 1, 2, 1, and that's square root of 1 squared, 2 squared plus 1 squared. That's square root of 6. Okay, and so the distance is just simply 7 over square root of 6. Okay. This could actually be solved using max-min principles. As time goes on in the course, we'll have enough math kung fu to be able to do that. You can set up a general distance formula from a point in the plane to here, and then this actually gives you the minimum distance considering all points in the plane. But we don't have enough multivariable calculus to be able to do that, so we just use a straight calculation. But it's nice to look back on this later on in the semester. And we can solve this as a multivariable max-min problem, get the exact same answer. the advantage of doing a multivariable max-min problem is we can actually find this point that minimizes the distance. Now it's interesting. We found the distance here, but it doesn't give us the point, it just gives us this length right here. So, okay, that's this. We'll be back shortly for a second video. We'll do a separate video on point to a line, and we'll be back shortly for that.